Welcome to the first session of Business Maths, where we'll be looking at the introductory aspect of calculus. Here, the main focus is to look at what is called differentiation, or the introductory aspect of differentiation, which is also part of calculus. The goals of this session is that at the end, we should be able to understand what a function is, examples of functions in a business, in economics, differentiation of a function, how to differentiate a function, and then how to differentiate a function from the first principle. We're looking at the rules under differentiation: constant rule, the power rule, the two or more functions of the same variable, also known as the sum or difference rule. We'll look at the product rule, the quotient rule, the chain rule, which has to do with composite functions that are not easily to be differentiated. So we use what is called the chain rule. Right. Here on our next slide, we have what is called a derivative of a function, or how to find a differential of a given function. This diagram here illustrates or shows how the first principle formula was brought about, or how we came about the first principle form. So think about this. Even if you are finding the gradient of a line from our basic school, we'll say we need 2 points with 4 coordinates, right? So here we have our y-axis, we have our x-axis, right? So it's the same idea of finding the gradient of a line, but here under differentiation, the idea is that we are looking for the slope of a tangent line to a curve. Remember, differentiation is a mathematical principle that is used to find the gradient or slope of a curve, right? So you are finding the slope of a curve or the gradient of a curve. So we also need 2 points with 4 coordinates. So I would say that the 2 points we have here are point P and then point Q. The first point P has 2 coordinates, A and then f of A. F of A is a functional notation. It's just writing this same A you have here, right? So we have A and f of A. So I could say that this A here is my x1. This f of A is my y1. And then I have a second point here, which is Q. I have coordinates z and f of z. Z here is my x2. F of z here is my y2. So I have 2 points here, and then with coordinates 2 here, 2 here, so 4 coordinates. Then I can find the slope of a tangent line to a curve, right? So what we'll do next is that we'll draw a straight line through these 2 points that we have. So a straight line through the points P and then point Q, right? This straight line over here is what we call a secant line. So take note, a secant line is a line that connects 2 points. So as you can see from this diagram, we would see that this straight line over here, which is called the secant line, is connecting points P and Q respectively, right? And then looking at this area over here, we'll see we'll have a distance here, right? We could say there's a horizontal distance here from P to the next point Q, right? Where we say the area of intersection, right? Here, this is where they will intersect. So from P here, there's a straight line here, which is called the horizontal distance to meet the second point Q. So we call this straight line the horizontal distance. The distance from what? P to the next point Q. This straight line is called horizontal distance. So we have coordinates for this distance as A and Z, isn't it? So from A to Z is what we call H, or from Z to A is what we call H. H is our horizontal distance, the distance between the 2 points, right? So we can go ahead and find the slope of a tangent line to a curve. The slope of a line PQ is equal to the gradient, or the slope of PQ is equal to f of Z minus f of A, right? It is the same idea. So I could say this formula over here, right, is the same as changing y over changing x, where the change in y is what? Y2 minus y1 over changing x is what? X2 minus x1. Here, y2 is f of z, and then y1 is f of a, all over x2 is what? Is your x2 is z, and then x1 is what? A. So that is the same idea you have here, right? That's the same idea you have here. And then the distance from z to a is what we call h, which is known as the horizontal distance. Take note that differentiation is a mathematical principle that is used to find the gradient or slope of a curve, right? Okay, so this is basically the idea or the formula of the first principle, right? We'll just change the alphabets or do some small changes here to get the final differentiation from first principle formula, right? So you can say that as scale moves along, isn't it? As scale moves along the curve towards P, Z approaches A, right? As scale here moves along the curve towards the point P here, you can say that Z here approaches what? A. That's what they are trying to say. This also means H approaches what? 0. Because when you have this, what's it called? When you have this, your graph over here, let's say a graph, right? The point 0 is here, right? So you can see that as this point Q moves along the curve to point P, this Z approaches A, or we can say H approaches what? 0, right? The slope of a tangent line at point A and then f of A is given as the limiting value of the slope. It simply means that this area here or this point P is the area of interest, right? That is going to help us to find the slope of this tangent line to the curve. Okay, so we need limits. Okay, so we say that to find the differential of any function or to find the derivative of any function, say 2x, or give any given function, we'll say that dy over dx is equal to the limit as z approaches a. Take note, z approaches a is the same as h, which is the horizontal distance. Our y2, which is what? F of z minus y1, which is f of a, all over x2, which is z minus x1, which is what? A. It is equal to the limit as h approaches 0, right? Because as z approaches a is the same as what? H approaching 0. Horizontal distance here approaching 0.0 here. Okay. So f into bracket a plus h is simply from this, let's say this function we have here or this term we have here. We say that from z to a, right? From z to a here is equal to our h. So z minus a is equal to h. We can just do what is called a change of subject here, and then we'll make z the subject. So making z the subject, we say that let z be equal to what? A plus h, right? So here in this formula, the z is being replaced with what? Or is being substituted with what? A plus h. It's just a basic change of subject, right? Minus f of a all over h, right? So this is the actual or we'll say the final formula for the differential of any function using the first principle formula. So therefore, the concept of the slope of a curve is the geometric version of the concept of a derivative. It's just telling you that to find the slope of any curve or any line tangent to a curve, we'll need what? These 2 points with 4 coordinates, right? To be able to find the slope or the gradient of the curve. Okay. Moving along, we will look at a bit tweaking of the formula, right? Still on the derivative or the differential of a function, right? The derivative of a function f is a function denoted by f prime, which is defined by. So any given function, right? Say f, okay, is the functional or is the function denoted with by f prime. It's simply telling you that when you have a function which is given to you, say f of x is equal to x squared, right? Say f of x is equal to x squared. Then to find the differential of that function, f of x is equal to x squared, we would say f prime of x. That means you are differentiating, or that means you are finding the differential of f of x, right? So say f prime of x is equal to 2x. So if you differentiate x squared, you get 2x. That's what I'm trying to say, okay? Provided the limit exist. So we would say that the limit as z approaches a is now being changed to x, right? Why? Because the question given to you will be given to you in terms of x. Say f of x is equal to x squared. The function is given in terms of x. So we are just changing the values of a to x in the formula. So limits as z approaches x. We say f of z minus f of x. Remember, it was f of a in the initial slide. It was f of a here, right? And then because the function will be given in terms of x, we'll say it's being changed to f of x, right? So all over what z minus a is now z minus x, right? So the final formula is saying that to find a differential of a function using the first principle, then as the limits h is approaching what? 0. Limits h approaching 0. F into bracket x plus h. Okay, remember we said z is equal to what? A plus h over here, which was found just making the change of subject here, making z the subject from this term or this function over here. We had z to be equal to a plus h. And because the term will be given, or the function will be given in terms of x, we would say that we are going to just change this a to be x, or we're going to replace this a with x. So therefore, we would have f into bracket x plus h, which is the same as z, right? Minus f of x all over h. Remember that z to x is equal to h, which is our horizontal distance. Remember, h is our horizontal distance. It's equal to f prime of x. So the final formula for differentiation from first principle, or finding the derivative of a function using the first principle, is that f prime of x, simply telling you that we are differentiating, f prime of x is equal to the limits as h approaches 0, right? As h approaches 0, f into bracket x plus h, right? F into bracket x plus h minus f of x all over your h, which is your horizontal distance, provided the limits exist, right? So if the limits exist, that is fine. That is maybe x is approaching 2 or x approaching 7, x approaching 5. But here, the limit doesn't really exist, right? So we'll say that h is approaching what? 0. Okay. So if f prime of a or f prime of what? X can be found, the original function f is said to be the differential at a. So if you have a function, say f, the differential of this f function is said to be f prime of a. If you are given a function, say f of a or f into bracket a, the differential of that function f of a is f prime of a. Okay, and f prime of a is called the derivative of f at a, right? So if you have f of a or f into bracket a, f prime of a is called the derivative of f at a, or the derivative of f with respect to x at a. Note, the process of finding the derivative of a function is called the process of finding the derivative of a function, right? The function is called differentiation, right? Right. So looking here, we have a basic example under differentiation, where we can use the first principle to find the differential of that function. So if f of x is equal to x squared, we've been asked to what? Find the derivative of f, or find f prime of x, right? We'll say find f prime of x. Okay. We asked to find f prime of x if the function notation of x is equal to x squared. So here we would use the first principle formula, right? We use the first principle formula, which is saying that to find the derivative of a function, it is f prime of x, simply telling you that we are differentiating. So f prime of x is equal to the limit of that function as h, limit of the function as h approaches what? 0. F into bracket x plus h minus your f of x all over h, which is your horizontal distance. Okay. So I'll take you through this whole f into bracket x plus h minus f of x all over h, right? This f prime of x here simply means that you are differentiating, okay? And the limit is that h is approaching what? 0, okay? So I'll take you through it one after the other. We have the numerator f into bracket x plus h. What does it mean? The f you are seeing here, right, represents the coefficient of the function you are being given or the function you have. What is the coefficient of x squared? We all know that the coefficient of x squared is 1, isn't it? So f here is 1, right? So that means it is 1 over here, isn't it? The x plus h is just the summation of your horizontal distance plus x. Okay. Why is it x plus h? You always, this x plus h over here is constant when the function given to you here has a component of x or the variable x in it. We can see that we have x squared here. So this function has a component of x. So we'll say 1 into bracket x plus h. Note that 1 into bracket x plus h. The x plus h is constant. You write the x plus h when the term given to you has a component of the variable x. Right. So it is 1 into bracket x plus h. But is the term raised to any power? Do you have any power on top of that variable you have over there? Yes. This x over here is being raised to the power 2. So I would say 1 into bracket x plus h, right, minus f of x. What is f of x? F of x is the same as the question itself, because it says f of x is equal to x squared. So I would say 1 into bracket x plus h all squared, because the function is raised to the power 2, minus x squared, right? So you can see it here as a limit as h approaches 0. So 1 times x plus h all squared is still x plus h all squared, right? So that would be x plus h all squared minus your f of x, which is what? X squared, all over your horizontal distance, right? So moving along, we would see that we would have to expand. The next thing is that you just expand what you have here, because you're having x plus h all squared. It means you're going to multiply x plus h by x plus h. And then when you expand that, you group like terms, right? You have x squared plus 2xh plus h squared. This over here, right? This term over here, x squared plus 2xh plus h squared, is the expansion of x plus h all squared. If you expand this function over here, right, you would get x squared plus 2xh plus h squared, then minus your what? X squared. Okay. What is the next thing? We would still write f prime of x is equal to the limit as h approaches 0. Then we can see that we have positive x squared here, we have negative x squared here. So this positive x squared will cancel this negative x squared off, leaving us with what? 2xh plus h squared all over our h, right? The next step is that looking at this numerator over here, 2xh plus h squared, it has a common factor, which is our h. So just do basic factorization. We'll factor h out, still having your f prime of x is equal to the limit as h approaches 0. We'll factor our h out, leaving us with 2x for the first term, plus leaving us with the h for the second term. Simply telling us that if you multiply h by 2x, we get 2xh. If you multiply this h over here by h, you get the h squared all over your h, right? So this h here, right, can do some cancellation here, right? We can cancel this h and this h. This h and this h will go off, right? Leaving us with what? The limit as h approaches 0, 2x plus h, right? 2x plus h. The next thing is that you are done with the factorization. You've been able to do some cancellations here with the h's, right? Numerator cancels the denominator. You are left with this. Now you are saying that the limit is that h is approaching 0, simply telling us that when you get to this particular point, the basic idea is that when you get to this particular point where you are done with cancellation of some of the terms which are like doing your factorization and then getting the final term, what you do is that you substitute 0 in place of h. It simply means that wherever you see h is approaching 0. So wherever you see h, you just put the 0 over there. So that will be our f prime, right? I could say our f prime, right? Our f prime of x, okay, is equal to what? 2x. Or we can also see that our f prime of x is equal to what? 2x. What does it tell us? It's telling us that the differential of this function, or to find the derivative of the function x squared, it is equal to 2x. Or the differential of the function x squared is equal to what? 2x. So take note, you can see that this is the function notation, or just the function. It says x squared. When you are differentiating, we would say f prime of x is equal to 2x. Okay. These are some common notations of a derivative of a function. It's simply telling us that, or it means that if you have a function, say y is equal to, say y, right? Say y is equal to x to the power 2, right? Say x squared, say x squared, right? You have a function, say so let's say we have a function, say y equals, say y equals y equals x to the second, right? If you have a function, say y is equal to x squared, like what you have here, it could be f into brackets x, or f of x, right, is equal to x squared. It can also be given to you as y is equal to x squared. It is the same. That's why initially you would have y is equal to f of x here in the diagram, right? Y is equal to f of x. The function can be given to you in terms of y. Say y is equal to x squared. It can also be given to you, say f of x is equal to x squared. They are the same. Right? That is why y is equal to f of x. So if it's given to you like this, then we would say to find a differential, we're not going to write f prime of x because we have y here. It's not f of x. So to differentiate that, we would say dy over dx. Okay. To differentiate this function, we'll say dy over dx. Okay. We'll say dy over dx is equal to what? 2x. This is the shortcut. Right. So instead of writing f of x, or instead of writing f of x here is equal to x squared over here, it's the same as y is equal to x squared. But if it's given to you f into brackets x, or f of x is equal to x squared, then the differential of this would be f prime of x is equal to 2x. But if the term is given to you, say y is equal to x squared, then we would say dy over dx. It simply means that the derivative of y, or the differential of y with respect to x, or the change in y with respect to x is equal to 2x. Right? So these dy over dx, these common notations, dy over dx, dfx over dx, y prime, dxy, dx, f of x, they are all the same as finding the differential of the function, right? f prime dy over dx. Depends on what you have here. So if it is y dy over dx, if it is f of x, we would say f prime of x. Okay. Right. Next up is to look at some of the rules under differentiation, some of the basic rules under differentiation. Okay. So the first rule we're going to talk about is what we call the constant rule. Okay. The constant rule, or what is called the constant function rule. The general idea for differentiation is that you multiply by the power, you reduce the power by 1. That's the general rule for differentiation. Multiply by the power, reduce the power by 1. What are you multiplying by the power? Multiply the coefficient of that function you are given, or the coefficient of the function you have, by the power of that same function. Then you reduce the power of the function by 1. So multiply by the power, reduce the power by 1. But if you are given a constant, okay, a constant could be, say you have y is equal to 5. The differential of 5, or the derivative of this 5 over here, is equal to 0. That's the constant rule. It says that anytime you differentiate a constant, it is 0. It goes away. Okay. So the derivative of, let's say, y is equal to 15, dy over dx will be 0. It goes away. If it's f of x is equal to 15, then we'll say f prime of x is equal to 0, right? So if you are given f into brackets, or say, we'll say f, right, into brackets x is equal to 15, then we would say that our f prime, right, f prime of x is equal to what? 0, right? Simply telling us that the differential of a function, say 15, which is a constant. Constant simply means that it is a number, or it is just a whole number without any variable attached to it. We don't have x here, right? So it is a constant. Anytime you differentiate a constant, it goes away. It turns out 0, so you don't write anything. You just leave it like that. It goes away, right? The second rule is what is called the power function rule, or the power rule. The derivative of a power function y is equal to f of x, which is equal to x to the power n. So we've been saying earlier on that y is equal to f of x, or f of x is equal to y, because the function can be given to you like this: y is equal to a function, or f of x is equal to the function. But when that function is being raised to a power, how do you differentiate it? So it says that dy over dx, right? So if it's given in terms of y, say you have y is equal to a function, you will say dy over dx. But if it is f of x is equal to a certain function, we will say f prime of x. Then we differentiate. So if you have x to the power n, how do you differentiate it? It is having a power of n here, right? So we say to differentiate x to the power n, it is multiplying the power by the coefficient. So the coefficient of this x to the power n is 1. Then n times the 1 will give us n. So it is n x raised to the power n minus 1. So it's simply multiply by the power, that will give you the n, then reduce the power by 1. That is what? N x raised to the power what? N minus 1. Multiply by the power, that's the coefficient of 1, by the power n. That will give us the n over here. Then x raised to the power, the same power, minus 1. Okay, that's how we differentiate a power rule or a power function, right? Okay. So an example is that find the derivative of y is equal to x to the power 4, right? This function here is raised to the power. It's a power rule that we're going to use, okay? So say dy over dx, right, is equal to multiply this coefficient of 1 over here by the power. That will give you 4. Then we'll say x raised to the power, the same power of 4 minus 1. Multiply by the power, reduce the power by 1, right? So that will give us 4x to the power 4 minus 1. That's equal to 4x to the third, or 4x cubed. Okay. The second example is to find the differential or the derivative of the function y, which is equal to 1 over x to the fourth. Right? We have been asked to differentiate this, or we have this function to differentiate. The whole idea is that to make it easier, okay, to make this function easier to differentiate, we will just rewrite this function. So it says that note that y is equal to 1 over x to the fourth is equal to x to the power minus 4. Right? Indices, isn't it? This has a power of 4, which is a positive value. If you rewrite this function, x to the power 4 comes up here, then the power becomes a negative value. So it is x to the power of negative 4. Therefore, we can differentiate this function now, right? It becomes easier because it's raised to a power, and then we can use the power rule. So we would say that dy over dx, because the function, you have y here, isn't it? So dy over dx, the differential of y with respect to x, so dy over dx is equal to negative what? 4x minus 4 raised to the power negative 4 minus 1. Multiply by the power, reduce the power by 1. The coefficient of 1 here multiplied by the power negative 4 gives us negative 4. Then x raised to the power negative 4 minus 1. That gives us what? Negative 4x to the power negative 5. You can leave your answer like this, fair enough, or you can go ahead and just rewrite it just to see how the question was given, right? So we would say this function here, or this term here, is the same as negative 4 over x to the fifth, right? This x has a power of negative 5. So indices, if it comes down like this, the power will be a positive value, right? So this is the final answer. Right. Okay, so let's continue. Note that since the derivative is a function of x, right, the derivative values of x may result in different values for the derivative. So if you differentiate a function and at the value of x you have say 2 or you have 3, then that means there will be different values for the derivative, right? So an example, practical example is here. Say the differential of x to the power 4, right? The differential of x to the power 4 is equal to 4x to the third, right? So if you differentiate x to the power 4, multiply 4, or the coefficient of 1 by 4, that will give us 4. Then x to the power 4 minus 1 will give us 3. That will give us 4x to the third. So having this, and then the value of x has been given at 1, right? Then that means f prime of x is 1, right? So in place of x, we just put 1 there. That will give us 4 times 1 to the third, right? 4 times 1 to the third, and 1 to the third is 1. So 4 times 1 will give us 1, right? Then at the value of x being equal to 2, then that means the derivative of that function at x being equal to 2 will replace 2 in place of x. So in place of x, we're going to put this 2 over there, and that will give us what? 4 into brackets 2, right? All raised to the what? The power 3. 4 into brackets 2 all raised to the power 3, right? And then we know that 2 to the power 3 will give us what? 8. So simply 4 times 8, that will give us 32. So we note that the derivative of the function that we have here at different values of x, it resulted in what? Different values for the derivative. At the point where x is equal to 1, we had the derivative to be what? 4. At the point where x was given us 2, the derivative of that function was what? A value of 32. Okay. The third rule under differentiation is what we call the generalized power function rule. Generalized power function rule. It's just a build-up of the power rule or the power function rule. But now you have a number which is greater than, let's say, 1 being your coefficient. Remember that when we did the power function rule, here we were having say x to the fourth, y is equal to x to the fourth, which is having a coefficient of 1. Under the generalized power rule, you could have the same x to the fourth or x to the third, but the coefficient is more than 1. So here you can say the coefficient of x cubed is what? 5, right? So for a function, say f is equal to the coefficient, that is the c over here, x to the power n. How do you find the derivative, right? So here, let me just change this to y. Okay, so here we have y is equal to x. Then we'll say that the derivative of y with respect to x will be dy over dx. We'll multiply this same power of, or the same coefficient here, c, by the power n. That will give us the cn over here. Okay, and then we have x to the power n minus 1. So simply multiply the coefficients by the power. C times n gives us cn, then x to the power n, which we have here, minus 1. Multiply by the power, reduce the power by 1. Okay, so an example is that f of x is equal to 5x to the third. To find the differential of this, we will say f prime of x, then we'll differentiate. Multiply the coefficient of 5, right? So the coefficient is 5. We multiply it by the power 3, right? Then we would say 3 minus what? 1. We'll say 3 minus 1. So coefficient is 5 here. 5, multiply it by the power is 3. So 5 times 3. Then x raised to the power, the same power of 3 minus 1. You see, we multiplied by the power, then reduce the power by 1. 5 times 3 gives us 15. Then 3 minus 1 gives us 2. So the final answer is what? 15x to the second, or to the power 2. Okay. This is another example under the generalized power rule, or the generalized power function rule, where we have a function, say y is equal to 4x to the power negative 3 or minus 3. Then we would say the differential of this function is such that dy over dx is equal to, what do? We multiply this same coefficient of 4 by the power of negative 3. That will give us 4 times negative 3. Then the power is what? Negative 3 already. So it will be 4 times negative 3, x to the power, right? We'll say x to the power what? Negative 3 minus 1. Okay, so 4 coefficients by the power, x to the power, the same, negative 3 minus 1. Negative 3 times 4, or 4 by negative 3, gives us minus 12. That is minus 12x to the power negative 4. And that is negative 3 minus negative 1. That will give us what? Negative 4, right? Let's look at the other rules under differentiation. Okay, so we have the third rule, which is called the sum or difference rule, or 2 or more variables of the same function, right? So sum or difference rule. Sum or difference rule simply means that you are given the function, but the binary operations there will determine how you go about it. Okay, maybe you have a first term, right? Say f of x plus g of x, or it could be f of x minus g of x. It means that you have two different terms over here, but it is being separated by a binary operation, which is maybe a positive or a negative. So to find the differential of that, it is saying that dy over dx, right, or f prime of x, differentiate the first function given to you. So if the first term is what? F of x, or yes, f of x, we would say dy over dx is equal to f prime of x. You've differentiated the first term. If the binary operation being separated, that is, the binary operation separating the two terms is positive or plus, we would say f prime of x, which is the differential of the first term, plus g prime of x, which is also the differential of this second term, g of x. So if you differentiate f of x, you get f prime of x. If the binary operation is plus, you bring it there, and then you differentiate g of x, you have what? You have what? G prime of x. So let's look at this typical example practical example under the sum or difference rule. We have an example which is saying find the derivative or find the differential of the function y equals 3x cubed plus 2x squared plus x. Well, we see that we have y over here, so definitely if you are differentiating, we would say dy over dx, right, which is already here. What we do is that we can see this is a function on its own, this 2x is also another function, and then this x is also another function. We have one term here, second term here, we have a third term here. So there are three terms over here being separated by a binary operation plus or addition, right? So we say dy over dx. Then we'll differentiate the first function. Multiply the coefficient of 3 by the power of 3, that will give us 9, right? Reduce the power of 3 by 1, that will give us 2. So the differential of 3x cubed is what? 9x squared. Then plus the differential of 2x squared. Multiply the coefficient of 2 by the power of 2, that will give us 4. Reduce the power of 2 by 1, that will give us 4x, 2 minus 1, which is the same as 4x to the power 1, which is also equal to 4x, right? Then the last term is what? X. If you differentiate x, you get 1. So the differential of x is 1, right? Okay. The differential of x is 1, right? So it means that the differential of the function y is equal to 3x cubed plus 2x squared plus x is equal to 9x squared plus 4x plus 1. That is the differential of the function. Okay. Remember, under business mathematics, we are just learning these basic rules or basic principles, right? Under differentiation or under calculus, then we apply it in the business sense. So we could have these rules being the standpoints, then you apply it, right? So we have what is called the application of differentiation. We're going to apply what we've learned here. Say we've been given an example like find the derivative of the total cost function, right? Which is giving us q cubed minus 4q squared plus 10q plus 75, right? We are being asked to find the derivative of the total cost function here. This is the total cost function. So what is it telling us? It's just telling us that we're going to differentiate the total cost function, right, which is C or TC with respect to quantity, right? I hope you can see that quantity Q here. So then how are you going to differentiate it? We'll say dC over dQ, the differential of the total cost with respect to quantity. Remember, if it is y here and then the variables over here are x, we'll say the differential of y with respect to x, so dy over dx. Here it is total cost and then we have quantity here, so it is differential of the total cost function with respect to quantity, so dc over dq. Then the same idea of differentiation, the general rule, multiply by the power, reduce the power by 1. Would say 3, we'll multiply 1 here, that will give us 3. Reduce the power of 3 by 1, we will say we have 3q squared. 4 by 2 will give us 8. So 8q, reduce the power of 2 by 1. It will give us 8q to the power 1 is the same as 8q. If you differentiate 10q, or the differential of 10q is 10. Right? So 10q, 1, right? 1 times 10 here. This, remember, this 10q is having a power of 1. So 1 here times the 10 will give us 10, right? And it will be 10q raised to the power 1 minus 1. 1 minus 1 will give us 0, right? So that is basically 10q raised to the power 0. And then any number raised to the power 0 is 1. So 10 times 1 will give us 10, right? Remember, we did what is called the constant rule. It says that the differential of any constant, any number without any variable attached to it, is a constant. If we differentiate that, it is equal to 0. It goes away, right? So the differential of the total cost function, q cubed minus 4q squared plus 10q plus 75 is equal to 3q squared minus 8q plus 10. That's the derivative of the total cost function. Note, if you differentiate the total cost function, right, the differential of the total cost function. So if you differentiate total cost function, it will give you what is called the marginal cost. Okay, the differential. So the D here means differential. So the differential of the total cost function, or the differential of any total cost function given, will give you what is called the marginal cost. So after differentiating this total cost function, we have this function here. This function here is the marginal cost function. So if you differentiate total cost, you get marginal cost. Okay. Okay, so let's look at the fourth rule, which is called the product rule. The product rule is used when you have two terms multiplying each other. We'll say given the function y is equal to f of x by g of x, then the derivative is expressed as dy over dx is equal to, so dy over dx is equal to f of x multiplying g of x, right? So f of x is multiplying g of x plus g of x multiplies your f prime of x, or yes. So I'm saying that the product rule, or say that the product rule is used, or at the time that we use the product rule, that means you have two terms multiplying each other. Say f of x is multiplying g of x. Okay, that's when we use the product rule. Product means times or multiplication. This is the formula for the product rule. It says pick the first term, right? Leave it as it is. Don't do anything to it. Multiply it by the differential of the second term. Plus, here you do the reverse of what you have here. So first term, keep it. Don't do anything to it. Multiply it by the differential of the second term. That is why it is g prime of x. Plus, remember it is product rule, multiplication. So the sign will change towards positive. Now, you keep the second term, right? You multiply it by the differential of the first term, which is f prime of x. Okay, so basically this is the rule for product. This is the product rule formula, right? So if you have two terms multiplying each other and you are being asked to differentiate, or you have to differentiate that function, what you do is that you are going to use the product rule, and this is the formula, right? This is not a maths class, so I would urge you to just ignore this, right? Because this is just a proof of how we got this formula. This is just going to show you the step-by-step approach of arriving at this final formula over here. So what you need is the formula, okay? Right. So you arrive at the same formula. If you go through that process, you will arrive at this same formula. So this is the formula that we need to be able to differentiate any function multiplying each other. So an example is that we are being asked to find the differential of the function f of x, right, is equal to x cubed plus 3x multiplying 4x plus 5. So here we can see that we have been given the function, but this first term over here, x cubed plus 3x, is multiplying 4x plus 5, right? So here we can use the product rule, which is saying that just represent one of the functions as f of x, represents the other function as g of x, right? So commonly, I will just say that let our f of x be the first term, which is what? X cubed plus 3x. And then we'll see the second term is g of x. So g of x is equal to what? 4x plus 5. Just represent the first term, f of x, the second term, g of x. Okay. Then the next thing is that we will just find the differential or the derivative of the functions we have. So you have f of x here. Find f prime of x, right? Because we need it in the formula here. We have to find g prime of x too, because it's needed in the formula here. So f prime of x is just differentiate this. The differential of x cubed plus 3x is what? 3x squared plus 3. And the differential of g of x, which is equal to 4x plus 5, will give us 4. Remember that this 5 here is a constant, it goes away. The differential of 4x gives us 4, right? What do? We have f of x, we have f prime of x, we have g of x, we have g prime of x. So just substitute them into the formula, right? So the differential, so f prime of x is equal to, keep the first term, which is x cubed plus 3x multiplied by the differential of g of x, which is what? 4. So 4 over here, plus keep the second term, which is what? G of x. So 4x plus 5 multiply it by the differential of the first term. So f prime, we had what? 3x squared plus 3, right? So the next thing is that you just expand this 4 into brackets, x cubed plus 3x, you expand that, you expand these brackets as well, and then you group like terms, right? So you would have 4x cubed plus 12x plus 12x cubed plus 15x squared plus 12x plus 15, then grouping of like terms, right? So we have some terms that are common, isn't it? So 4x here plus 12x cube here will give us 16x cube, right? Then the next thing is we have 15x squared, then 12x plus 12x will give us 24x. So just grouping of like terms, then plus 15, right? So this is the final answer. So it's telling us that the differential of the function x cubed plus 3x multiplying 4x plus 5x is equal to 16x cubed plus 15x squared plus 24x plus 15, right? Okay. So this is another example under the product rule. You can try your hands on this at a convenient time, right? Just to get the concept. This is just the same procedure. This will be my f of x, this will be my g of x, right? I'll find my differential for the first, that is f prime of x. I'll find the differential of my second term, which is g prime of x. I'll just substitute it into this formula. I'll expand it, group like terms, then I have my final answer. So this should be your answer, right? Okay. Let's look at the next one, which is the quotient rule, right? The next rule is quotient rule. So we've done the product rule. Product rule has to do with two terms multiplying each other, right? They are multiplying. Quotient simply means division. So this is where you have a function, but they are divided by they are being divided with a division sign. So you have one term dividing the other term, right? So you can have, say, f of x is equal to f of x over g of x, right? So dy over dx. So this is also the formula for using the quotient rule. We use the quotient rule as well when you have two terms dividing each other. So the first term is divided by the second term, right? So this is the formula. It says that it is keep the second term, right? So if I have something like this, I will say this is my lower term, this is the higher term. So it is keep the lower term, which is g of x, multiply it by the differential. So I'm going to multiply it by the differential of the higher term, which is f of x. That gives us f prime of x. And because it's quotient and it's a division, it's going to change to what? Minus. Then we'll do the reverse of this. Keep the first term or the higher term, which is what? F of x. Multiply it by the differential of the lower term, which is what? G prime of x, right? So keep the lower term, multiply it by the differential of the higher term, minus you keep the higher term, multiply it by the differential of the lower term, all over the lower term, all squared. Okay. So there is another way of just getting the concept or remembering this formula, right? So this is how we do it. I would say low d high, right, minus high d low, right, over low low. So this is another way of just getting this formula into your medulla, right? So if you don't remember this and then you're able to just keep this mnemonic name of head, you'll be able to write this formula, because I say low the high minus high the low over low low. Low means the lower term. The high means differentiate the higher term, right? Low means the lower term. The high means differentiate by the higher term. So keep the lower term, multiply it by the differential of the higher term, minus hide the low simply means that keep the higher term, which is probably your numerator, multiply it by the differential of the lower term, so the low, which is the differential of your denominator, then your denominator all squared. So I could say that this over here, right, is my high, okay, and then g of x here will be my low, okay. So I'm going over this again. Let me go over this again. So f of x here is my higher term, g of x is my lower term. So I would say low the high, keep the lower term, which is what? G of x. That's why you have it here. Multiplied by the differential of the higher term. If you differentiate f of x, you get what? F prime of x minus, now you keep the higher term, so high, f of x, which is here. Multiply it by what? The low, by the differential of the lower term. If you differentiate g of x, you get what? G prime of x all over what? Low low. So g of x, sorry, all squared, right? Okay, so you can keep this also off head so that you can easily remember this formula over here, right? So this is also the process of going about it to arrive at this final formula of the quotient rule. So this is the formula that we need for quotient rule, right? But this is the process of going through to arrive at this final formula over here. Okay, so let's pick a practical example here, which is saying that f of x is equal to 4x squared plus 3x all over 2x minus 1. We are supposed to find the derivative of this function f of x. So find what? F prime of x. So you can see that this, we have two functions dividing each other. 4x squared plus 3 is dividing what? 2x minus 1. This is the solution, or how to go about it. I would say this is my what? F of x, right? 4x squared plus 3 is my f of x. 2x minus 1 is my g of x. Then I'll go ahead and find the derivative of both. So I would say the differential of f of x is what? F prime. If you differentiate 4x squared plus 3, that'll give us 8x. Then if you differentiate 2x minus 1, that'll give us 2. Then the next thing is just substitute it into this formula that we have over here. It says keep the lower term, which is g of x, 2x minus 1, multiplied by the differential of the higher term, 8x, minus keep the higher term, multiply it by the differential of the lower term, then you divide it by the lower term all squared. So we have f prime of x. They're just telling us that we are differentiating. So we expand this, we'll have 16x squared minus 8x minus bracket of 8x squared plus what? 6 all over 2x minus 1 all squared all over low or g of x squared, right? 16x squared minus 8x minus 8x squared minus 6 all over 2x minus 1 all squared. The next thing is that we are going to group like terms, right? So we just group like terms here, right? X squared, we have 8x minus 8x, 8x squared minus 8x minus the 6 all over 2x minus 1 all squared. Right? So this is the final answer. So the differential of the function 4x squared plus 3 all over 2x minus 1 is equal to 8x squared minus 8x minus 6 all over 2x minus 1 all squared. Right. So this is a second example that you can try on home. So to enhance your understanding, right? So just give it a try. Keep this as your f of x, this is your g of x. Find the differential of both, substitute it back into this formula, expand group like terms, and then you are good to go. Okay. So we are here on the next slide where we have the consumption function and the slope of the average cost curve, right? So let's look at the consumption function first. The consumption function expresses a relationship between the total national income I, or the total income I, and the total national consumption C. That is, C is equal to F of I, right? So consumption is equal to the function notation of your income, right? So this expresses the relationship between the total income I and the total national consumption C, which is written as what? C is equal to the functional notation of your income. Okay, this means that your consumption is a function of your what? Of your income. That's the meaning of this. Your consumption is a function of your what? Your income. Right. The next thing is your marginal propensity to consume. The marginal propensity to consume is defined as the rate of change of consumption with respect to income. That is the derivative of consumption with respect to income. That is the WRT, with respect to income. Marginal propensity to consume measures how much consumption changes with a change in income, right? The marginal propensity to consume, or MPC, measures how much consumption changes, right, with respect to what? A change in your income, right? And that is defined as the derivative with respect to your what? A change in income, right? That's what you have here. So marginal propensity to consume is your DC over DI, right? So derivative with respect to your what? Income. So DC over the DI. So how much you consume is dependent on your income, right? Okay. So if savings S is the difference between income I and what? Consumption C, then savings is equal to your income minus your consumption. So how much you have as your income minus the consumption value, right, will give you what is called the savings. So that's the savings function. Savings function is that S is equal to income minus consumption. Okay. The derivative of savings with respect to income is the marginal propensity to save. Okay. The derivative of S, which is your savings, with respect to the income is the marginal propensity to save, which is expressed as ds over di, right? So the MPC, or the marginal propensity to consume, is ds over di, a change in your savings with respect to your income. Or we would say it is 1 minus your marginal propensity to consume. 1 minus your marginal propensity to consume. So 1 minus our MPC, right? 1 minus MPC will give us what is called the marginal propensity to save. Okay. And note that the marginal propensity to save, or the MPS, measures how much savings changes with respect to a change in your income. So how much you save as an individual is dependent, or is dependent on the income that you're receiving at the end of the year or the end of the month, right? So if you are receiving 1,000 Ghana cedis and you consume 200 Ghana cedis, right, that means that the savings value you have, or what you'll be left with as savings, is just 800 cedis, right? Okay, so marginal propensity to save measures how much savings changes with a change in your income, right? That is it. Right, so it is the S over the I. So the changes in income with respect, changes in your savings with respect to what your income, based on your consumption. So the MPS or the marginal propensity to consume is 1 minus your marginal propensity to consume. So your marginal propensity to save, MPS, okay, is equal to 1 minus what? DC over the I, which is the same as 1 minus your what? Your marginal propensity to consume, right? This is a practical example, right? You can try your hands on it. Right? It's just the same idea of using the quotient rule, because you have one function dividing another function. You can use the quotient rule. So if the consumption function is C, 5 into brackets 2 root I cube plus 3 all over I plus 10. Determine the marginal propensity to consume and the marginal propensity to save when your income is 100 cedis or $100, any of them, right? Okay, so you can use the quotient rule because you have one term divided another term. You just find your MPC, right? One becomes your f of x, the other becomes your g of x. Find the differential, substitute it into the quotient rule formula. You arrive at the final term or the final function of your MPC, where you just substitute this 100 in place of I. So wherever you see income or I in the MPC that you have after using the quotient rule, you just put the 100 over there, and that will give you the value for your MPC. Right? So when you have your MPC, you can find your MPS. Remember, your marginal propensity to save is equal to 1 minus the marginal propensity to consume. Right? So say you have the marginal propensity to save, or your MPS as, you have your MPC as 0.54. That's for your marginal propensity to save. Your marginal propensity to consume at 0.54, then you can simply find your marginal propensity to save, or your MPS, as 1 minus your MPC. So that will be 1 minus 0.54, and that will give us what? That will give us 0.46. So practically, I'm saying that if you have your MPC, so using the quotient rule will give you the final function of your MPC, and say after finding your MPC function, you substituted income, that is I, into the function, and you had MPC to be 0.54. We can go ahead and find our MPS. Right? You can go ahead and find our MPS, which is equal to what? 1 minus our MPC. So marginal propensity to consume is 0.54. Therefore, we can find the marginal propensity to save to be 1 minus what? MPC. And that is equal to 1 minus 0.54, right? And that is equal to 0.46, right? 0.46. Right, so let me go over this again. You have the consumption function. What you do is that the numerator is your f of x, denominator is your g of x. Find the differential of f of x. That is, find your f prime of x, find your g prime of x, substitute it into the quotient rule formula, and that will give you your MPC. So after getting the MPC function, wherever you see I or income in that function, you put this 100 cedis over there, and that will give you your marginal propensity to consume. That should be 0.54. Let's say 2 decimal places, right? And then you can go ahead and find your marginal propensity to save, which is 1 minus your MPC. 1 minus 0.45 or 54, will give you 0.46, right? So that's how you go about this particular question. Okay, looking at the right hand side of the slide, where we have the slope on the average cost curve. Remember that the slope of the average cost curve depends entirely on the relationship between the marginal cost and then the average cost. Okay, note that the slope of the average cost curve, right, depends entirely on the relationship between the marginal cost function and then the average cost function. That is the whole idea of this particular slide over here on the right hand side. So suppose the total cost function is C, that is C into bracket Q, where the C is your total cost function, and then Q is the quantity produced. Then we'll say that the average cost function is what? The total cost function over quantity. So simply saying that the average cost to get your or to find your average cost function, it is equal to your total cost over quantity, right? For quantity being greater than 0. Note that quantity is greater than 0 because we can't produce negative units or negative product. So always the quantity should be greater than what? 0, right? Okay. So we have something here which is talking about the rate of change of the average cost with respect to quantity. Is giving us the C over the Q, right? Here is just using the quotient rule formula. So we'll see it is C prime multiplying your Q, right? C prime of Q multiplying Q minus C Q, right? Multiplying 1. So C prime of Q multiplying Q minus CQ multiplying 1 all over Q squared. That will give you this, right? Then you have this. So it says the C over the Q, that is the total cost function over your quantity, is greater than or equal to 0 if and only if the total cost function is greater than or equal to the average cost. The differential of the total cost function with respect to quantity is greater than or equal to 0 if and only if the differential of that total cost function is greater than or equal to the average cost. Okay, and then this one is talking about the C over the Q. So the differential of the total cost function with respect to Q, which is the quantity over here, is less than or equal to 0 if and only if the differential of that total cost function is less than or equal to the average cost function, right? So since the derivative of the total cost function is the marginal cost function, so this is simply telling us that if you differentiate the total cost function, that will give you your marginal cost function. So the differential or the derivative or the total cost, the differential or the derivative of your total cost function is equal to your marginal cost function. And total cost function, that's C into bracket Q or TC over Q, is the average cost function. Right, so to get your marginal cost function, it's simply differentiating the total cost function. And to get your average cost function, it is simply dividing your total cost function by quantity. The economic meaning of the two if and only if relationship is that the slope of the average cost curve will be positive, 0, or negative if and only if the marginal cost function lies above, intersects, or below the average cost curve. This is talking about the rate of change of total cost with respect to quantity, right? That is the cost of producing one more unit, right? The cost of producing one more unit has to do with the marginal cost. Remember, what we have here is a relationship between the marginal cost and then the average cost. And earlier when I said that the slope of the marginal cost function is dependent, or it depends entirely on the relationship between what? The marginal cost and then the average cost. What we have here, right, both the functions and then the explanations over here simply is telling us that when the marginal cost, right, when your marginal cost is greater than average cost, right, that is greater than 0, right? When marginal cost is greater than average cost, that is greater than 0, then we'll say the average cost function is rising. I hope you get that. If the marginal cost is greater than, so marginal cost greater than average cost simply means that it is greater than 0, so the average cost function is rising. Second one is that the marginal cost function, if it is less than the average cost function, then we would say the function over there is less than 0, and that also means that the average cost function right, is also falling. Okay, and then the third option is that when the marginal cost function is equal to the average cost function, or MC is equal to AC, then we would say that that point it is equal to 0, and that is the minimum or maximum point. We will say that AC is at a minimum, or the average cost is at a minimum or maximum point. I'll take it again. This whole scenario or this explanation over here simply means that you could have a point where the marginal cost function is greater than the average cost function. That is, your average cost is greater than what? 0. It's simply telling you that the average cost function is what? Is rising at that point, because MC is greater than what? AC. Right? And then the second point is that when the marginal cost is less than your average cost, simply means that at that point, the average cost is less than 0. It's just telling you that the average cost function is what? Is reducing or is falling at that point. And then the last one is that where MC, or the marginal cost, is equal to average cost, their points AC is equal to 0, or AC is at a minimum or the maximum point, right? So this is the explanation on the slide we just spoke about, right? It's just an explanation to this relationship between marginal cost and average cost function, right? Okay, so we see it is here, the relationship between marginal cost and average cost function. So this function over here, these two functions, MC function, AC function, or this graph over here, simply represents the cost analysis, right? Which is focusing on what? MC and AC. This is representing the cost analysis, right? Focusing on what? Our marginal cost function and the what? Average cost function. So on the x-axis here, right, which is the horizontal line, represents the quantity, right? This horizontal line here, which is our x-axis, represents the quantity ranging from 0 to 10. This is our x-axis. It represents what? The quantity. So Q, ranging from what? 0 to 10. And then on the y-axis over here, which is the vertical line we have over here, it represents the cost. Okay, this represents the cost ranging from what? 0 to 140. Okay, so let's go back to this curves over here. This is the marginal cost function. This is the curve. This is the average cost function. This is the curve. So the orange curve we have here, represents the what? The marginal cost curve. This is the marginal cost curve, which is the what? The orange curve we have here, or the orange line, I would say, represents the marginal cost curve. Okay, which is what? U-shaped. Okay, so we could see that initially it decreases, right? Initially it decreases. It decreases initially, right? And it reaches a minimum point, right? It was decreasing initially, then it reaches a minimum point over here, then it increases sharply, right, to this end. Okay, so this is the marginal cost curve, and we could see that initially it decreases, and when it gets to the minimum point, it increases at a faster rate, or sharply, I would say. Okay, so the minimum point occurs where the derivative of the marginal cost function with respect to quantity is equal to 0. Right? So the minimum point I'm talking about here, where they intersect, is the minimum point. You see, minimum point 6, value is 24, right? So the minimum point here occurs where the derivative of this marginal cost function is being equated to 0. That will give you the minimum point. So I would say that we have the marginal cost function here to be 3q squared, right? 3q squared minus 24q plus 60. The differential of this of this will give us 6q minus 24. And then if we have 6q, right, minus 24 being equated to 0, we would have our quantity being equal to 6. And that is our minimum point, right? So we will say that MC is lowest at quantity being equal to 4. At quantity being equal to 4, right? Because if you have the differential of this 3q squared minus 24q plus 60 as 6q minus 24 being equated to 0 will give you a quantity of 4, right? So you can see that MC here is lowest at what? 4. You see that it decreases from this point to 4, then where the 4 is our minimum point. That is after differentiating the marginal cost function, equating it to 0, you get 4. So you say MC is lowest at 4. And then you see that it decreases up to 4 over here, then it increases sharply over here, right? So MC is lowest at 4. That is a minimum point for the marginal cost function. Looking at the average cost function too, we would say that the average cost function is q squared minus 12q plus 60. The average cost curve is also the gray curve we have over here on the marginal cost curve, right? This is a gray curve over here, is the average cost curve, right? It is also U-shaped. Unlike the marginal cost curve, you see the marginal cost curve is U-shaped, but that one, it goes up a bit because when it gets to the minimum, it rises from there sharply or goes at a faster rate. But that of the average cost curve is U-shaped too, but it is flatter than the marginal cost curve. You can see that the average cost curve is flatter than the marginal cost curve, even though it is also U-shaped, right? So from here, we can also find the minimum point of the average cost curve, or the minimum point at which the average cost occurs, right? So that one, so what you do is that we'll find the derivative or the differential of the average cost. So differentiate q squared minus 12q plus 60. That will also give us 2q minus 12, right? And then 2q minus 12 will give us a quantity of 6. It's also telling us that MC, right, this is AC, which is the average cost curve, is lowest at what? The point 6. Okay, that is basically the idea. For MC, it is lowest at the point 4. That the differential being equal to 0 gives us a quantity of 4. AC is lowest at 6. The differential of this AC function being equal to 0 will give us a quantity of 6. So basically, that is the explanation to this diagram over here, right? So when MC is less than AC, then we'll say that what? AC is falling. When MC is less than AC, we'll see that AC is falling, right? When MC is less than AC, we'll say AC is falling. And then when MC is rather greater than AC, here we'll say that the AC or the average cost curve is rising, right? And then when the MC curve is equal to the AC curve, this is the intersection point. Where they intersect, that point is the minimum point, right? Where they intersect. So when MC curve is equal to the AC curve, this is the point of intersection at point 6, right? As a quantity of 6, we would say MC is equal to AC, right? We'll move on to the next slide where we have the chain rule, okay, which is also another rule under differentiation, but has to do with composite functions. It has to do with what is called composite functions. Why am I saying this is a composite function? And why are we using the chain rule? We are using the chain rule because sometimes you'll be given a function like this, y is equal to x cubed minus 1 all raised to the power 7. It becomes very difficult to differentiate using the normal differentiation rules that we've learned, the constant, product, quotient rule, and then the rest, right? It becomes very difficult to do that. So what you do is I use what is called the U-substitution or the chain rule. Okay, this is how you go about the chain rule. It's an old rule. From convention, it has been this. So it is dy is the rule. It is dy over dx. That is, find the differential of such functions. It is dy over du multiplying du over dx. That's the chain rule formula. Dy over dx is equal to dy over du multiplying du over dx. So an example here, this is a composite function. Y is equal to x cubed minus 1 all raised to the power 7. What this means is that to differentiate this, you can use a shortcut though, but let's do it the normal way by using the chain rule, right? You can use the shortcut to solve this, but let's use the normal way of differentiation, right? To make it a bit easier for us to go about, right? So we would say this function x minus x to the power 3 or x to the third minus 1 is a function on its own. The 7 over here is a function on its own. To use the other rules that we've learned earlier, then we have to multiply this x to the power 3 minus 7. We'll multiply it 7 times, group like terms, get a single term before we can differentiate. I hope you get that. We have to expand this 7 times before we can use the normal rule of differentiation, right? We have to expand this 7 times before we can do the normal differentiation. Okay, so we'll say we represent one of the functions with u. Normally we represent what is in the bracket with our u. So we'll say let u be equal to x to the power 3 minus 1. Remember, from the formula we need dy over du, we need du over dx. So let u be equal to what is in the bracket, right? So we'll say differential of this will give us 3x squared. We rewrite the question. The question is saying y is equal to, now we said x cubed minus 1 is equal to u. So it is u to the power what? 7. Then we can find dy over du, which is 7u to the power 6. What to do is that we just back substitute. We just put these two functions, 7u to the power 6, 3x squared, back into the chain rule formula over here. And that will give us this. 7u to the power 6 by 3x squared. Right? Then we'll put the actual term of u. Note that we said u is equal to x cubed minus 1, right? And that will give us dy over dx being equal to 7 into bracket x cubed minus 1 multiplying, all to the power 6 multiplied by 3x squared. That is the final answer. Same applies to this. The same procedure. Let u be equal to what is in the bracket. Differentiate that function. Rewrite the function again. Y is equal to u to the power 10. Differentiate that as well. Substitute it back into the chain rule formula and you will have your final answer. Right. Right. So the next thing is that we're looking at some rules and a differentiation, right? Which has to do with what is called special functions. Special functions are functions, they are also rules and a differentiation, but that's where we have what is called the natural logarithm and you have what is called the exponential functions. So let's look at the first aspect of the special functions, where we have the natural log. Natural logs has to do with your ln, right? So you can have something like y is equal to natural log of x or ln. How do you differentiate something like this? To differentiate that, we would say it is 1 over u times du over dx. That is the formula to differentiate any natural log function. So it is 1 over u times du over dx, or I would say 1 over the function times the differential. 1 over the function times the derivative of that function. The function is when we close this, right? When I remove this ln from there, or ln, what is left is x. X is the function. So if you have ln x to the power 2, the function is x squared. If you have ln x, the function is x, right? So it is 1 over the function times the differential of that same function. Here, the function here is x. So an example is that y equals natural log of x squared plus 5 all squared. Right, so it is 1 over the function. What is the function? The function is, when I take off this ln, what is left is x squared plus 5 all squared. That is the function. So let u be equal to x squared plus 5 all squared. Now we'll differentiate this using the chain rule, or we can use the shortcut. What I'll do is that I'll differentiate u with respect to x, but it's raised to the power 2. So I can use the chain rule, or there's a shortcut to use the chain rule. I would say that bring the power here in front of the function. That will give you 2 into bracket x squared plus 5. Reduce the power of 2 by 1. That will give us 1 over here. Then I'll multiply it by the differential of what is in the bracket. So if you differentiate x squared plus 5, you get 2x. So you bring the power in front of the function, 2 into bracket x squared plus 5. Reduce the power of 2 by 1. You have 1 here. Then you multiply it by the differential of what is in the bracket. If you differentiate x squared plus 5, that will give you 2x. And that's the d over the x that you need over here. So you can just substitute it into the formula. So dy over dx, 1 over u. So 1 over the function. 1 over the function, which is x squared plus 5 all squared. Multiply it by du over dx, which is what? 2 into bracket x squared plus 5 multiplied by what? 2x. 2 by 2 will give you 4x, right? Then over 4x into bracket x into 4x into bracket x squared plus 5 all over x squared plus 5 all squared. So 2 by 2 will give you 4. Multiplied by this will give us 4x into bracket x squared plus 5 all over x squared plus 5 all squared. Remember that x squared plus 5 over here will cancel one of these x squared plus 5. So we have dy over dx being equal to 4x over x squared plus 5. Right, that's how we deal with the natural log as a special function. And we have what is called the exponential function. Under the exponential function, which is also a special function, we can have something like y equals e to the power x. The idea is that anytime you have an exponential function, if we differentiate that exponential function, you get the same answer. So if you differentiate y equals e to the power x, you get e to the power x. Right, you get e to the power x. So it says that to differentiate any exponential function, it is dy over dx. So dy over dx is equal to keep the function as it is. Right, you keep the function as it is. So if it is e to the power x, this value which is on top, or what is on top of the e, is the function. So here I'll say that the function is what? X. That is why you have e to the power u here. So keep the function as it is, multiply it by the differential of that function. So here the function is x. So I'll say let u be equal to x. That's why you have e to the power u here, right? Times du over dx. If you differentiate x, you get 1, right? So this is a better explanation. It said let u be equal to x. So to choose your u, to select your u, it is what's on top of the e. That is let u be equal to x. Du over the x. Du over the x here will give us 1. If you differentiate x, you get 1, right? So that will give us e to the power u. So e to the power u times 1, right? Because this e to the power u times the differential. So e to the power u times 1 will give us e to the power u. Then we'll just back substitute and we'll say that u is equal to x, right? U is equal to x. So we'll say that dy, right? So we'll say dy over dx is equal to what? E to the power x. It is equal to e right to the power x. So that's it. That's how we do with exponential function. That's why I'm saying that the differential of an exponential function e to the power x will give you the same e to the power x. Keep the function as it is. Don't do anything to it. It's just changing here because you said that the u, which is the function here, is the x. So keep the function as it is. multiply it by the differential of that function. If you differentiate x, you get 1, which is here. And then it will give you the same thing. If you back substitute, put the actual term of u here. You say u is x. That's giving us the same thing, right? Well, so let's look at the other parts of the special functions where you have an exponential functions, but a bit different from what we did earlier. So here we have y equals e to the power x squared plus 1 all squared, right? Note that if you have an exponential function that differentiated, you get the same exponential function. So this function e to the power x squared plus 1 all squared, if you differentiate this, we'll get the same thing. So the idea is that, first of all, you write the question itself. So I would say dy over dx. And differentiating y with respect to x over here. So dy over dx is equal to, then I write the function again, e to the power x squared plus 1 all squared times the differential, right? So the differential is what's on top of the e. So if I cover this e over here, what is left is the outer function. I would say that is x squared plus 1 all squared. So I'll differentiate that either by using the chain rule or the shortcut. Bring the power in front of the function. Then I'll write x squared plus 1. Then I'll multiply that 2 by the differential of what is in the bracket. So take it again. Bring the 2, which is the power, in front of the function here. And we have x squared plus 1, brackets close. We use the power by 1. So here we have a power of 1 here. You can decide to write it. You can leave it like that. It's the same, right? Then you multiply it by what? The differential of what is in the bracket here. So the derivative or the differential of x squared plus 1 is 2x, right? The derivative of x squared plus 1 is 2x. Then the next thing is that we have dy over dx. We have the same function. We write it again because if you differentiate, you get the same thing. We multiply it by 2 times 2x will give us 4x. So 4x into bracket x squared plus 1. And that is the differential of the function y equals e to the power x squared plus 1 all squared. This is the final answer here, right? This is the final answer here. Keep the function as it is, because if you differentiate it, you get the same thing. Now you multiply it by the differential of what is at the top of the e, right? Keep the function as it is. Multiply it by the differential of what is on top of the e, which is x squared plus 1 all squared, and that'll give you 4x into brackets x squared plus 1, right? So you can try this at your leisure time, right? You can try this example here. You should be able to go about it because it's the same example here, right? So you just try and solve this as well to get a final answer looking like this, right? So we'll move on to the next slide, which is the rate of change and the derivative of a function. The rate of change and the derivative of a function. So when two or more variables, say x and y, are related to each other by a function y equals f of x, right? I've been saying from the inception that y equals x squared is equal to f of x is equal to x squared. So the term or the function can be y equals the function or f of x equals to the function. But take note that if it is y is equal to x squared, then we'll say that the differential will be dy over dx is equal to 2x. But if the function is given as f of x here is equal to x squared, then we'll say f prime of x is equal to 2x. Right? If you are given f of x is equal to x squared, then we'll say f prime of x is equal to 2x. That means the differential of that function is 2x. Okay. There is always an interest in the changes in one variable to a change in the other variable, right? When the variable x changes from x0 or x subscript 0 to x subscript 1, the change is measured by the difference between x1 and x0, or x1 minus x0, using the symbol here, right, to denote the change, right? Use this small triangle here to denote the change, okay? right? So the change in x, if I am changing x, it is what? X1 minus x0. Unlike, it's just like finding your gradient and then you have a change in x, right? It is x2 minus x1. So here it's x1 minus x0. We use f into brackets xi to denote the value of the function, right? F of x when x is equal to xi. Isn't it? So the rate of change here, we often want to know how much y changes when x also changes, right? The area of focus is that we want to know how much y changes when x also what changes. So the change in x over here, right, is just saying that if x, right, over here changes from x1 to x0, then the change in x is equal to what? X1 minus x0, right? So if x, right, if x changes from x0 to x1, then we'll say the change in x is what? X1 minus x0. That is just representing a change in x we have here. And when it comes to the change in y too, the same application. So the change in y is the difference in the function value, right? So that one will be change in y is equal to f of x1 minus f of x0, right? When it has to do with change in y, okay? When it has to do with change in y, we'll say that it is f of x, right? F of x1 or I, okay? Minus f of x0, right? Okay, so this is how we'll go about it with the change in y. The change in y is the difference in the function value. That is, change in y is what? F of x1 minus f of x0, right? So here you could see that we say we use f of xi to denote the value of the function f of x when x is equal to what? Xi. So an example here, given f of x is equal to 5 plus x squared, here our x is equal to 0, then we'll just put the 0 here in place of x over here. So that will give us 5 plus 0 squared, and then 5 plus 0 squared is 0. 5 plus 0 will give us 5. Then what if the value of x is being changed from 0 to 2? We'll see that in place of the x now, we'll replace it with 2. So that will give us 5 plus 2 squared, that is 5 plus 4, which is equal to the 9 we have here, okay? So you see that as the value of x changes, the value of the differential also changes. Okay, so when it was 0, we had the value to be 5. When it moved to 2, now we have the value to be 9. So when x changes from an initial value of x0 to a new value, that is the x0 plus the change in x, then the function y is equal to f of x also changes from what? X0 to f of x0 plus change in x. Is a change in y per unit of change is x, which is represented by the difference quotient, right? The change in y per unit of change in x is represented by the difference quotient. That is change in y over change in x. This is basically the first principle formula that we learned earlier, right? So it is change in y over change in x, f into brackets x0 plus the change in x minus f of x0 all over change in x, right? So change in x over change in y, simply dy over dx is equal to f into brackets x0 plus change in x minus f into brackets x0 all over the change in x. So I would say this is the same as f into brackets x plus h minus f of x all over h, which is our horizontal distance. Thus, the difference quotient can be calculated if we know the x0 and change in what? X. So the difference quotient over here gives the rate of change of y with respect to x. The rate of this difference quotient over here gives us the rate of change of y with respect to x. That is why it is changing y over changing x. This is just a foundational concept in calculus, especially when you are studying what is called derivatives, right? So the difference quotient here simply gives us the rate of change in y with respect to x, right? So on our next slide here, this is just to show an example that builds on the concept of the difference quotient, which just talks about the rate of change in y with respect to x, right? It's an example that builds on the concept of the difference quotient to show how to calculate the average rate of what? Change. The average rate of change, the average rate of change of a function over an interval, right? This is just showing how the difference quotient works, or how it is used to calculate the average rate of change of a function. So here we have y equals 3x squared minus 6, right? So we'll say 3 into bracket x 0 or x subscript 0 all squared minus 6. And then our f of x 0 plus change in x is 3 into which 3 is the what? The coefficient of the first term, which is what? 3x squared. Coefficient of this 3x squared is 3. So 3 into bracket x0 plus what? Change in x all squared minus the 6 we have here, right? So just substitute this into the formula, right? So we have the same formula here, 3 into brackets x0 plus change in x all squared minus 6. Remember, this 3 into brackets x0 plus change in x all squared minus 6 is just representing f into brackets x0 plus the change in x. And then minus f of x0 is the question itself, or is the function given to you, which is what? 3x squared minus 6, or 3 into brackets x0 all squared minus 6, right? So if you do our normal cancellations here by grouping like terms, we would have this. We would have 6x0 change in x plus 3 into bracket change in x all squared all over the change in x. From here, you can see that we have change in x here, change in x here as a common factor. We can factor change in x out, right? So we'll have change in x into bracket 6x subscript 0 plus 3 change in x all over change in x. Here, the numerator, there is a change in x here, there's a change in x here, all squared, right? So we can say that the common factor here, so by simple factorization, we'll factor change in x out, leaving us with 6x over here, leaving us with plus 3 change in x over here, all over what? Change in x. The change in x here will cancel the what, the change in x we factored out, right? So this change in x here will cancel this, leaving us with what? 6x subscript 0 plus 3 change in what? X. Okay. To leave us with 6 subscript 0 plus 3 change in x. So therefore, the change in y over change in x, or the average rate of change, can be calculated for known values of x0 and what? The change in x. Simply h, x, and then what? Your h, if it's given to you. If the horizontal distance is given to you and the value of x is also given to you, the initial value of x is given to you, and then you have the horizontal distance, you can calculate the values for this function. For example, if x0 is equal to 5 and then the change in x is equal to 2, we would say that the change in y over change in x is equal to what? 6 by 5, right? Is equal to 6 by 5 plus 3 times what? 2. So it means that in place of this x0 over here, we will replace that with, or we substitute that with 5, right? Plus 3, then the change in x here is now 2. So in place of this change in x, we'll put the value of 2, and that will give us 6 times this 5 here, which is also here, plus 3, which is here, by the change in x, which is 2, right? So by 2, and that will give us 30 plus 6, giving us a 36 value, final value here, right? So note that x0 is the initial value or initial value of x. Change in x is simply your horizontal distance. Okay. So this final answer of 36 means that on average, when x changes from 5 to 7, right, the change in y is 36 units per unit change in x. I'm taking it again. This means that on average, as the average rate of change, when x changes from 5 to 7, the change in y is 36 units per unit change in your x value, right? So here you can see that initially we're having an initial value of x to be what? 5. Then the change in x here is what? 2. So it means that 5 plus 2 gives us what? 7. So it moved from 5 to an additional value, this plus this, giving us 7. So from 5 to 7, the change in y is 36 units per unit change in the value of x. It also means that for every 1 unit increase in x, y increases by 36 on average over that interval. Right? So for every 1 unit change in the value x, right, y also changes or y also increases by 36 units, right? For every unit change in x, y here increases by what? 36 units on average over that interval. Okay. So looking at the last level, last part of the session over here, we'll look at the derivative of a function. It's just talking about the rate of change, the average rate of change, or what is called a difference quotient, right? So this explains how fast y changes with respect to x. And we use this by, this is found by using a limit, right? So we are looking at how fast y, right, changes with respect to what? X, right? So think of it like this. If you zoom in close on a curve, right? If you zoom in close on any curve, the slope at a point becomes clearer, right? That slope is a derivative. So if you zoom in really close on a curve, the slope at that point on a curve, right, becomes clear. That slope is the derivative of the function, or is the derivative of your given function. Or we could say that the derivative is the exact rate at which a quantity changes, found by what? Zooming in infinitely, right? Infinitely close and taking the limits of the change ratio. I'll take it again. It also means that the derivative is the exact rate at which a quantity changes, found by zooming in infinitely close and taking the limits of the change ratio. So most times we are interested in the rate of change of y when change in x is very small. So how fast is this y going to change with a change with respect to this x, right? How fast is this y changing with respect to this x over y? So in such cases, it is possible to obtain a change in y over change in x, which is the average, by dropping all terms of the change in x in the difference quotient formula, right? For the last time, we'll look at this. It says that, for example, in the last example that we did, right, if change in x is very small, then the change in y over change in x is approximately 6 by 30, right? It's approximately 6 by 30. So saying that if we had this initial value of x to be 5, then we had no value here for the change in x. It means that the value of the change in x is very small. It could be 0. So say this is 0, change in x here is 0. Then we are left with 6, right, by x0, which is 5 here, plus 3 multiplied by 0 over here, that will give us 0. So 6 by 5 is approximately what? 30. That is what this is trying to say, right? For example, if the change in what? X is very small, right? Then the change in y over change in x is approximately 6 by 5, which is equal to 30. The smaller the value of the smaller the value of change in x, the closer is the approximation of what? Change in y over change in x to the true change in y over change in x. So the closer the value of this, assuming it's 0, we would have this being equal to or being approximately 30, which is very true to the average, right? As the change in x approaches 0, meaning that it gets closer and closer to, but never really reaches the value 0. So 6x subscript 0 plus 3 change in x will approach 6x to a subscript of 0, right? That is a 6 by 5 giving us the 30. So symbolically, this statement is expressed as change in y over change in x approaching 0, or change in x approaching 0, or by the equation. You see, I said that we find this, or explaining how fast y changes with respect to x, it is found by using a limit. So we say the limit of the change in x approaching 0, that is the change in y over change in x. It is 6x subscript 0 plus 3 a change in what? X. But you can see that here you see that the limit is such that change in x is approaching 0. So wherever we have change in x, it's going to be replaced by the 0 automatically. Let's put it in that way to make it very simple and clear. So that will be 6 subscript 0 plus 3 times 0, and that will give us 6 subscript 0 here, right? So the symbol LIN represents your lim, that is change in x approaching 0, is read as the limit of change in x, right? The limit of the function as the change in x approaches 0, right? So the limit of that given function as the change in x, right, approaches 0. If say change in x approaches 0, the limit of the difference quotient change in y over change in x exists. That limit is identified as the derivative of the function y equals f of x. That's what I was saying. So if that change is being really looked closely, right? You zoom in really close on that curve or on that limit that's identified. The slope at that point becomes clear, right? And then that slope is what we call the derivative of the function, right? So the slope on that curve becomes the what? At that point becomes the derivative of the function. So we would say y equals f of x, or f of x is equal to y, right? Thank you. See you another time.